Welcome back to the Cave of Science, and today we're going to look at activation energy. And activation energy is the minimum amount of energy that causes a reaction to occur. And the first type of reaction we're going to look at is an exothermic reaction, where heat is released to the surroundings. So we're going to do a couple graphs with this. So let me see if I can change my pen here. And on the x-axis and y-axis. On the x-axis is the reaction progress. So the reaction is going this way. And on the y-axis is potential energy, or chemical potential energy, PE. And so let's look at the curve of an exothermic reaction. So we're going to draw a curve in here and then we'll go through it. All right. So right here we have the reactants. And down here we have the products. Notice the reactants are at a higher potential energy than the products. So we need to decipher this curve. So the potential energy that lies between the reactants and the top of the curve is referred to as the activation energy. This is the energy that is needed to get the reaction to occur. Now, the amount of energy from the reactants to the products. So we're looking at the products are here. This amount of energy, remember you always got to count for energy. Energy can't be destroyed nor created. It can only transfer. And so this is the energy that is released, energy released to the surroundings. Now remember, when energy is released to the surroundings are going to feel warm. They're going to feel warm to the touch, or sometimes they'll even feel hot to the touch. So exothermic energy is released. So this is the activation energy from the reactants to the top of the curve, and then from the reactants to the products is the energy released to the surroundings. Now, you got to remember, delta H is enthalpy. And another way you could think about this is our delta H. When it is an exothermic reaction, delta H is going to be less than 0. So if you want to say this is the system, the box is the system, then energy is released to the surroundings. So think of the box as the system, and the energy is released to the surroundings, so the surroundings get warm. So the surroundings get warm. And that would be your typical exothermic reaction. So let's look at the other general type of reaction. If I get this to go, there we go. So let's look at an endothermic reaction. Try a different color here. An endothermic reaction. So when we have an endothermic reaction, it requires energy from the surroundings. An endothermic reaction requires, or needs, if you will, requires energy from the surroundings. And let's go ahead and, for endothermic, let's go ahead and look at our graph for an endothermic reaction. So if we get that down a little bit, yeah, it looks pretty good. So we'll do another graph here. So this is our reaction. This is going to be our potential energy, our chemical potential energy. Now for an endothermic reaction. The products are going to be at a lower potential energy, or excuse me, the reactants are at a lower potential energy than the products. So here we have our reactants. Here we have our products. Let's go ahead and put in our activation energy. And our activation energy is from reactants to the top of the curve. So let's look at that. So our activation energy is going to be from the reactants to the top of the curve. So this is going to be our activation. And notice for an endothermic reaction, our products, which are here, we're going to have to somewhere gain this energy. So where's this energy going to come from? This energy is going to come from the surroundings. So this is energy that is absorbed. Energy from surroundings. Because we've got to find some energy, because the energy of the products is higher at a higher state than the energy of the reactants. Well, so this energy's got to come from somewhere, and for an endothermic reaction, it's got to come from the surroundings into the system. So if we were to look at that, we could say delta H, our enthalpy, is going to be greater than 0. And again, our box is the system. So energy from the surroundings is flowing into the system. So if the energy from the surroundings is flowing into the system, that means the surroundings are getting cooler. Because the energy is flowing into the system. It can only come from, it's going to either come from the reaction itself, or it's going to come from the surroundings where the reaction's taking place. And for an endothermic reaction, it's flowing from the surroundings into the reaction. So that's why you would see the products are going to be at a higher energy level than the reactants here. All right, that's it for this one. On the next one, we're going to throw a catalyst into the activation energy and see what happens to the amount of activation energy with the catalyst. All right, so until next time.